I need to tell you about something that has haunted me throughout my entire career as a physicist. This isn't about quantum mechanics, even though that's strange enough. This isn't about relativity, despite its mind-bending implications. This isn't even about the origin of the universe, though that's certainly mysterious. No, the mystery I want to share with you cuts deeper than any of these. It's more fundamental, more pervasive, and in many ways more disturbing than anything else in physics. The mystery is this: why does nature obey mathematics? Think about that question for a moment. Why do equations predict reality? Why does calculus describe motion? Why do differential equations govern everything from the behavior of atoms to the movements of galaxies? An electron doesn't know calculus. It has never taken a mathematics course. It doesn't solve equations in some tiny notebook. It doesn't compute integrals or manipulate symbols. And yet, its behavior follows equations. Not approximately, not roughly, perfectly, exactly, always. How is this possible? Why does it happen this way? This question haunted me my entire life, keeping me awake at night, nagging at me during quiet moments, resurfacing whenever I successfully predicted some phenomenon using mathematics. And I never found a truly satisfying answer. Nobody has. But I learned something profound in the attempt to answer it. Something about the nature of reality itself, about the nature of mathematics, and about the mysterious relationship between these two things. Let me share with you what I discovered, what I struggled with, and what still fills me with amazement after all these years. The strange precision of natural law. Start with a simple observation, a fact so obvious that we barely notice it most of the time. Nature follows rules, not vague guidelines, not approximate tendencies, precise rules, mathematical rules. Drop a ball from your hand, it falls. How fast does it accelerate? Exactly 9.8 meters per second squared at Earth's surface, every single time, according to equations that were written down centuries ago. Not approximately, not roughly, exactly. Run electric current through a wire. How much current flows for a given voltage? Exactly the amount predicted by Ohm's law. Precise, mathematical, predictable down to as many decimal places as you can measure. Light passes through a lens. Where does it focus? Exactly where the equations predict, every single time, without exception, without approximation, with perfect mathematical precision. This is deeply strange when you stop to think about it. Why should reality obey human mathematics? Why should equations that we invented in our minds, symbols we scribbled on paper, match what actually happens in the physical world? What's the connection? Eugene Wigner, a brilliant physicist, wrote what might be the most important paper on this subject. He called it "The Unreasonable Effectiveness of Mathematics in the Natural Sciences." Pay attention to that word, unreasonable. It's the key to everything. It's not reasonable that mathematics works so well. It's not expected. It's not something we should take for granted. It's miraculous. It's mysterious. It's unexplained. Wigner gave example after example in his paper. Mathematical concepts developed for pure theory, abstract explorations with no connection to physical reality, later turn out to describe nature perfectly. Let me give you some cases that particularly struck me. Complex numbers were invented by mathematicians trying to solve certain equations, just pure mathematics. Beautiful, elegant, but seemingly with no physical meaning whatsoever. They were numbers involving the square root of -1, which doesn't correspond to anything you can count or measure in any obvious way. Then quantum mechanics comes along, and it turns out that electrons, actual physical particles, are described fundamentally by complex numbers. Wave functions, the mathematical objects that describe quantum states, are complex valued. Complex amplitudes are essential, fundamental, unavoidable. You cannot do quantum mechanics without complex numbers. How did mathematicians invent exactly the right mathematics decades or even centuries before physicists needed it? Coincidence? Perhaps one coincidence could be dismissed, but there are too many coincidences, far too many. Group theory provides another striking example. This is abstract algebra, the study of symmetries and transformations developed as pure mathematics. Beautiful, intellectually satisfying, but seemingly useless for understanding physical reality. Then particle physics comes along and discovers that symmetries are absolutely fundamental to understanding the subatomic world. Gauge symmetries, Lie groups, representation theory, all of this abstract mathematics turns out to be exactly what we need. Everything in particle physics is organized according to group theory. We classify particles using these mathematical structures. Perfect match. And here's the astonishing part. The mathematicians had already worked all of this out decades earlier for completely different reasons, with no thought of physics applications. Why? How is this possible? This is the mystery that Wigner was pointing toward, the unreasonable effectiveness. Mathematics works better than it should. It works better than we have any right to expect. And every physicist who works deeply with equations feels this mystery, whether they articulate it or not. The moment of wonder. I felt this mystery deeply, viscerally throughout my career. Every time I derived an equation and found that it matched experimental results, every time I predicted something using mathematical reasoning and nature agreed with my prediction, I felt a sense of wonder mixed with profound puzzlement. Let me tell you about one particular moment that crystallized this feeling for me. It was 1948. I was working intensely on quantum electrodynamics, trying to develop a new formulation of how light and matter interact at the quantum level. I was attempting to calculate something specific, the magnetic moment of the electron. The calculation was brutal, absolutely brutal. Pages and pages of integrals, Feynman diagrams, which I had just invented, covering my blackboard and my notebooks, complex numbers everywhere. And worst of all, infinities kept appearing in my calculations. Infinities I had to remove through a tricky process I was developing called renormalization. The work took me weeks. I made mistakes, got confused, started over, made different mistakes, persisted. Finally, after an enormous effort, I got an answer, a prediction. The electron's magnetic moment should be slightly different from the simple textbook value. Not hugely different, just a tiny deviation. About 0.1%, I was nervous, genuinely nervous. This was a bold prediction based entirely on mathematics, on my new formulation of quantum field theory, on techniques nobody had used before. If the prediction was wrong, my whole approach might be fundamentally flawed. Years of work could be worthless. We tested it. Experimentalists measured the electron's magnetic moment with as much precision as they could manage, carefully, meticulously, and the result came back. It matched exactly to every decimal place we could measure. I remember sitting there staring at the numbers, my hands shaking slightly. How? How did my mathematics, my human symbols on paper, my invented formulas and diagrams predict what an actual electron would do? An electron that doesn't know calculus, that doesn't know about Feynman diagrams, that doesn't know mathematics at all. And yet it behaves exactly, precisely, perfectly according to my equations. That moment, that realization, that's when the full force of the mystery hit me. It was too good, too perfect, too mysterious to be mere coincidence or accident. Why does the universe speak mathematics? Why doesn't it speak some other language entirely, or no language at all? Why is it comprehensible in this particular way? I don't have a complete answer. I don't think anyone does, but I have thoughts, observations, patterns I noticed over decades of wrestling with this question. The mathematics of economy. First observation, nature uses principles of economy, optimization, and efficiency. This is everywhere in physics, and it's deeply, inherently mathematical. Consider the principle of least action, one of the most profound principles in all of physics. When a particle moves from point A to point B, it doesn't take just any random path. It takes the specific path that minimizes a particular mathematical quantity called the action. Why? Nobody knows. But it does, always, perfectly. Light traveling through different materials takes the path that minimizes travel time. This is Fermat's principle. But why? Light doesn't have a brain. It doesn't know calculus. It doesn't compute anything. Yet it finds the optimal path every single time without fail. Think about this carefully. Really think about what's happening. A photon enters a piece of glass from air. It needs to reach a point on the other side. There are infinite possible paths it could take. The straight path through air and then through glass, not optimal because it spends too much time in the slow glass. A path that's straight in air and then straight in glass, not optimal either, unless the angle is exactly right. The actual path the photon takes is bent at the interface between air and glass, bent at precisely the angle that minimizes the total travel time. Exactly the right angle, not approximately. Exactly. How does the photon know which angle to choose? It doesn't calculate. It doesn't try different paths and compare the times. It doesn't think or compute, but it chooses perfectly, every single time, the mathematically optimal path. In my path integral formulation of quantum mechanics, I found a way to explain this that satisfied me somewhat. The photon, in a sense, tries all possible paths simultaneously. Each path contributes a quantum amplitude. These amplitudes interfere with each other. And the path that contributes most strongly, the one where nearby paths have similar phases and similar actions, turns out to be exactly the minimum time path. So in the quantum mechanical picture, the photon does explore all paths, and the interference automatically, naturally selects the optimal one. Beautiful, elegant, mathematical. But even this doesn't answer the deeper question. Why? Why does nature work this way? Why this particular mathematical structure? Why this optimization principle? Why this economy? Optimization is mathematical, inherently, fundamentally mathematical. Concepts like minimum, maximum, and optimal are mathematical ideas, and nature uses them everywhere, in everything. I once said that nature uses only the longest threads to weave her patterns. What did I mean by this? Not longest in a literal sense, but most fundamental, most economical, most elegant. Nature doesn't waste. She doesn't complicate things unnecessarily. She chooses the simplest, most elegant solution to every problem. And here's the remarkable thing. Simple and elegant turn out to be mathematical properties. The beauty of fundamental equations. The equations that govern nature are beautiful. They're symmetric. They're economical. They're not arbitrary or unnecessarily complicated. Take Maxwell's equations, which describe all of electromagnetism, every phenomenon involving light, electricity, and magnetism, every single one. And how many equations do we need? 4. Just 4 elegant, symmetric, beautiful equations. Why 4? Why not 40? Why not 4,000? Because nature is economical. She uses only what's necessary, nothing more, nothing less. And economy, it turns out, is a mathematical property. Minimum principles everywhere, symmetries everywhere, conservation laws everywhere. And there's a deep connection between these things revealed by Noether's theorem, one of the most beautiful results in all of physics. Emmy Noether proved that every symmetry in nature corresponds to a conservation law. Time symmetry, the fact that the laws of physics don't change over time, corresponds to energy conservation. Space symmetry, the fact that the laws are the same everywhere, corresponds to momentum conservation. Rotational symmetry corresponds to angular momentum conservation. Mathematical symmetry equals physical conservation. One-to-one correspondence, perfect, exact, universal. Why? Why should symmetry, which is an abstract mathematical concept, correspond to conservation, which is a concrete physical fact? Nobody knows. But it does, always, without exception. This suggests something profound. Mathematics isn't just a convenient description that we impose on nature from the outside. It's somehow built into nature, woven into the fabric of reality itself, fundamental to what reality is. The deepest question, discovery or invention? But here's the question that haunted me more than any other, the question I could never satisfactorily answer. Does nature really use mathematics? Or do we just describe nature using mathematics? In other words, is mathematics discovered or invented? If mathematics is discovered, then it exists independently of us. It's out there, part of the universe, and nature is genuinely mathematical at its core. We just find the equations that already govern reality, uncovering what was always there. If mathematics is invented, then it's our creation, a language we made up to help us think and communicate. And the fact that it describes nature so well is what? Coincidence, selection bias, something else? I struggled with this question my whole life. I never reached a firm conclusion. The question kept shifting, slipping away from me, looking different, depending on which angle I approached it from. Sometimes I felt absolutely certain that mathematics must be discovered, that it must be real and objective. The equations are too perfect, too exact, too universal for it to be otherwise. I remember a student asking me once, a bright kid at Caltech, after one of my lectures on quantum mechanics. He raised his hand and said, "Professor Feynman, do you think mathematics exists independently of humans? Is it discovered or invented?" I thought about it for a moment, paused, and then said, "Ask me an easier question like the meaning of life." He laughed. The other students laughed, but I was completely serious. This question genuinely seemed harder to me than almost any other question I could think of. Here's why the question troubled me so much. An electron in my laboratory at Caltech behaves exactly the same as an electron anywhere in the universe. Same charge, same mass, same behavior, same equations governing it. How would that work if the equations were just our human invention, our made-up symbols? How would electrons in the Andromeda galaxy, 2 million light years away, know to follow our human mathematics? They don't know about humans. They've never heard of calculus. They don't care about differential equations. They don't even know that humans exist. But they follow the same equations exactly, perfectly, always. This strongly suggests that the mathematics is real, objective, built into reality itself, independent of us and our minds. But other times I thought maybe mathematics is invented after all. Maybe it's a tool we created, and it works well simply because we only apply it where it works. We find patterns and regularities in nature, and we invent mathematical structures to describe those patterns. We don't try to use differential equations to describe human emotions or love or the experience of listening to music or consciousness. Why not? Because mathematics doesn't work well there. It doesn't capture what's essential. So we only use mathematics where it does work, where it's applicable. Selection bias. We see mathematics everywhere in physics because physics is specifically the study of things that are mathematical, things that follow quantitative laws. Things that aren't mathematical, that don't follow precise equations, we don't call physics. We call them something else. Psychology, art, philosophy, whatever. Maybe nature isn't fundamentally mathematical at all. Maybe we just focus exclusively on the mathematical parts and ignore or set aside everything else. But that explanation doesn't feel right either, because the mathematical parts of nature are so fundamental, so basic, so unavoidable. Motion, force, energy, light, matter, these aren't obscure or specialized phenomena. They're everything. They're the foundation of physical reality. So maybe both perspectives are true in some strange way that I can't quite articulate. Mathematics is a language we invented, a system of symbols and rules we created. But the patterns that mathematics describes are real, objective, universal, independent of us. It's like how English is an invented language, but the things English describes, mountains and rivers and stars, are real. The words are invented. The referents are discovered. Perhaps equations are invented, but what they describe, the relationships, the patterns, the regularities, those are discovered. The map is not the territory, as they say, but the territory has genuine structure, and our map reflects that structure, captures it, represents it. I don't know if this resolves anything, but it's how I gradually came to think about the question over the years. A different way to frame the mystery. Here's another angle, another way to approach the fundamental mystery. Maybe the question itself, why does nature obey mathematics, is poorly framed. Maybe it assumes too much. Perhaps nature doesn't obey mathematics. Perhaps mathematics is simply our way of capturing regularities, of describing patterns. Wherever there's a pattern, a regularity, a consistency, we can create mathematics to represent it. And nature clearly has patterns, lots of them, deep patterns, universal patterns. So of course mathematics works, because mathematics is what we call the systematic description of patterns. It's almost a tautology. It would be like asking, why does nature obey language? Nature doesn't obey language. Language describes nature. We observe something and we create words to talk about what we observed. But wait, this still doesn't explain the deeper mystery. It doesn't explain why the patterns are so mathematical, so precise, so exact, so consistent. A ball falls. We can describe its motion with equations. Fine, but why does it fall the same way every single time? Why is the acceleration precisely 9.8 meters per second squared, not varying randomly, not different on Tuesdays, not dependent on the ball's color or history? The consistency, the regularity, the lawfulness, that's what needs explaining. Why isn't motion chaotic, random, different each time? Why does nature follow rules at all? And that mystery remains, even if we say that mathematics is just our description of those rules. The mystery is why there are rules to describe in the first place. Living with perfect predictions. I spent my entire professional life working with equations, deriving them, manipulating them, using them to make predictions, teaching them to students. And the more I worked with equations, the more mysterious they became to me. Not less mysterious. More mysterious, because I saw over and over again how perfectly they worked, how exactly they predicted, how universally they applied. I derived quantum electrodynamics, the theory that eventually won me the Nobel Prize. The equations I developed predict electron behavior to 10 decimal places. 10 decimal places. Perfect agreement between theoretical prediction and experimental measurement. That's not approximate. That's not rough. That's not close enough. That's exact as far as we can possibly measure. How is this possible? Why does it work this way? An electron doesn't know my equations. It doesn't study Feynman diagrams. It doesn't integrate over all possible paths. It doesn't compute anything. But it behaves exactly as if it does all of these things. Exactly. This amazed me when I first realized it. It still amazes me today. It will always amaze me no matter how many years I spend working with these equations. The path integral formulation that I developed says sum over all possible paths that a particle could take. Each path contributes a quantum amplitude. Add up all these amplitudes and you get the probability of finding the particle at a particular location. I derived this mathematically, pure mathematics. Integrals over infinite dimensional spaces, complex numbers, action functionals, abstract, formal, mathematical. And it works perfectly. Electrons actually behave as if they explore every possible path simultaneously and sum the quantum amplitudes. How do they know to do that? They don't. They can't. They don't have brains or computation devices or any mechanism for following instructions, but they do it anyway. The mathematics describes what happens exactly, perfectly, universally. This is the mystery. This is what I never fully explained. This is what nobody has explained. Why does the universe run on mathematics? Why is reality computable? Why do equations work? De Metz, is the universe made of mathematics? Here's a radical possibility that sometimes occurred to me, usually late at night when I was working alone. Maybe the universe itself is mathematical. Not that it uses mathematics, but that it is mathematics. What is mathematics really at its core? Its patterns, relationships, structures, abstract patterns, abstract relationships, abstract structures, independent of any particular physical instantiation. And maybe that's all reality is too. Patterns of energy, relationships between particles, structures in space-time, not things that obey mathematics, but things that are mathematics, fundamentally made of mathematics at the deepest level. This sounds mystical when I say it out loud. It sounds like philosophy rather than physics. But maybe it's true. Maybe asking, why does nature obey mathematics, is like asking, why are circles round? They just are. That's what a circle is. Roundness is part of the definition. Maybe reality is mathematics. That's what reality is, fundamentally. Not two separate things, the same thing viewed from different angles. But even this perspective doesn't fully satisfy me, because mathematics can describe many things that don't exist, that aren't real. I can write down equations for particles that don't exist in our universe. I can describe possible universes with different physical laws. I can do mathematics about purely imaginary scenarios. So why does this particular mathematics, these specific equations, these particular patterns, correspond to this particular reality that we observe? Why these equations and not other equally valid mathematical structures? Why these patterns and not different patterns? Why this universe and not some other possible universe? You might invoke the anthropic principle here. We observe this particular universe because we exist in it. If the universe were different, we wouldn't be here to ask the question. Selection bias again. Maybe. But that feels unsatisfying to me, like dodging the question rather than answering it. The mystery remains. Deep, fundamental, unresolved. The beautiful mystery. I, Richard Feynman, worked with mathematics and physics for more than 50 years. I explored quantum mechanics, quantum electrodynamics, particle physics, and many other areas. I derived equations, made predictions, tested theories, taught thousands of students. And through all of that, through all those decades of work, the deepest mystery wasn't quantum mechanics, despite its famous weirdness. The deepest mystery wasn't relativity, despite its counterintuitive implications. The deepest mystery wasn't even the origin of the universe, despite the profound questions it raises. The deepest mystery was this: why does nature speak mathematics? I don't know the answer. Wigner didn't know. Einstein didn't know. Nobody knows, even today. But I learned to live with the mystery. More than that, I learned to appreciate it, to be amazed by it, to find wonder in it rather than frustration. Every equation that matched experimental results, every prediction that came true, every time the mathematics worked when it had no right to work, I felt the wonder. I felt the astonishment. I felt grateful for the privilege of glimpsing this strange relationship between human thought and physical reality. Maybe we're not meant to understand why mathematics works. Maybe that's not the kind of question that has an answer. Maybe we're only meant to appreciate that it does work and to marvel at that fact. And it does work beautifully, precisely, mysteriously. Nature uses only the longest threads to weave her patterns, I said. The most fundamental threads, the most economical, the most mathematical. Why? I genuinely don't know. But I'm grateful that it's true, because those mathematical patterns let us understand the universe far more deeply than we should be able to. They let us predict the future, explain the past, manipulate matter and energy, build technologies, cure diseases, explore the cosmos. That's what Wigner meant by unreasonable effectiveness. We don't deserve to understand reality this well. We don't deserve to have mathematics work this perfectly. But it does. That's the miracle. That's the mystery. That's the wonder of it all. Mathematics works. Nature obeys it. Or is it? Or something. We're not sure which. We describe nature using mathematics. We predict using mathematics. We understand using mathematics. And that's miraculous, truly miraculous, when you stop to think about it. The universe speaks mathematics. And somehow, mysteriously, we humans learn to speak that language too. We learn to read the equations written into the fabric of reality itself. Why is this possible? Why does reality have this structure? Why is mathematics the key? Mystery, beautiful mystery, profound mystery, eternal mystery. But what a beautiful mystery it is. What an incredible privilege to be aware of it, to work with it, to spend a lifetime exploring it. And now you know it too. Now you've glimpsed the deepest question in all of physics. Now you understand why, despite everything we've learned, despite all our progress and all our theories, we still stand in awe before the fundamental nature of reality. The universe speaks mathematics, and we still don't know why.